Hi, my name is Duncan Mays, and I'm presenting Diverge by Yang. Convolutional neural nets are vulnerable to what are known as adversarial attacks. So these are what is essentially static that is added to images that can make these CNNs produce false classifications. And this is a really big problem in production settings for obvious reasons. Imagine if somebody could put up a sign that made Tesla's autopilot freak out and take some kind of drastic action. It could hurt people in that case. And what's scary is that these vulnerabilities are unique to the data set, not architecture or model parameters. And so if somebody has access to the data set that you trained your CNN on, they can produce a surrogate model that will share vulnerabilities, and so they can still develop these adversarial attacks. In the words of Ilias et al., adversarial vulnerabilities are unavoidable and even important for clean accuracy. They are a feature, not a bug. Diverge operates on what are known as ensembles, and an ensemble is a combination of many submodels that all evaluate on samples independently, and then their prediction on each sample is combined somehow, usually through averaging. In Diverge, each of these submodels was trained to have different adversarial vulnerabilities, and so this meant the ensemble as a whole would be more robust. Diverge was benchmarked on CIFAR-10 using ResNet 20 as submodels, and it simply averaged the output. It didn't apply any kind of weighting to them. And they used four separate techniques. They used Diverge, they used a baseline technique, which was a simple ensemble with nothing fancy, and they used two other state-of-the-art techniques known as ADP and GAL. And their metric for success was the success rate of adversarial attacks. As an intermediate result to show what Diverge is all about, of the set of adversarial examples that are effective against one submodel in the ensemble, only about 3 to 6% worked on any of the other submodels. And so Diverge was successful at training submodels with diverse vulnerabilities. The authors also found that better robustness corresponds with more submodels. And you can see a chart on the bottom of this slide that gives that relationship. The three top red lines are Diverge. The blue lines underneath it are GAL, which was the next best technique, and then the black line at the bottom is the baseline tests. So you can see that Diverge is much more effective than any other technique available. Now, Diverge is quite expensive. I mean, ensembles are quite expensive. The training resources, the time and compute needed scales with the number of submodels, and it's still not a perfect method. As the chart above shows, the vulnerability of CNNs increases with the scale of the static, and that would make the image seem distorted, but that's acceptable in a lot of cases. Adversarial training, which is a more common approach, needs only one model and only reduces accuracy by around 10%. But the model can be made wider to account for this, and it would only train the training resources by a fraction of what Diverge would. And so in my opinion, to reduce adversarial vulnerabilities in CNNs, better options exist than Diverge. An interesting avenue for future research could be if this is applied to mixtures of experts. So mixtures of experts are really similar to ensembles in that there are many submodels that evaluate independently, but they differ in that for each sample, only one submodel is run. And so they're much more resource efficient than ensembles in both training and evaluation. If Diverge could be applied to mixtures of experts, it would solve Diverge's resource problem. Thank you for your time. I hope you enjoyed the presentation.